Okay. Let's start. So finally, the last time we didn't get to it, but today we can get to the topic of scheduling. Any questions meanwhile before we start? Good. Everyone is trying to survive. The next homework, yeah. So I should write it. So I'll try to start today. Hopefully, release the first draft tomorrow. But let's see. Easy, but let's see. Like I'll try to like do a meaningful draft, but usually it takes like two full days to finish writing. So, but we should get going. Okay, so scheduling. Okay, what is the goal of this scheduling algorithm? What do you guys think? What are we trying to achieve? Jesus Christ, you know the word fairness. Okay, sure. Okay, what is fairness? Say equal. So let's imagine we run 3 threads, 1, 2, and 3. Intuitively, I mean, like honestly, I mean, on the surface, it looks very simple. If you start digging, the concept of fairness is very, very complicated. So I'm not exactly sure how to even, I'm not sure it's solved. What these systems are doing, they say, look, we'll divide time into slices, right? And of some lengths. And roughly speaking, like even higher up. So like fairness, on average, each of these threads should be given like 1/3 of a CPU, right? So that's intuitive definition of fairness, right? Okay, sure. If we want to implement this intuitive definition of fairness, what do we do? I actually don't mind this. Let's start with this fair.
Timer to preemptively interrupt every 1/3.
Okay, for sure. And remember, this is where the timer interrupts homework comes handy. What Talia said, she said, okay, instead of like interrupting every 10 milliseconds, for example, we can be a little clever and we can say, look, guys, we know that we can configure timer in this specific mode when you can say like interrupt us in some number of cycles. And instead of like doing this in a modern kernel, we can say, look, really interrupt us after some amount of time, right? And meaning that we don't have to like follow a fixed timer. We just say, look, if we choose the slide to be 100 milliseconds, for example, we'll divide by 3, so whatever it is, it's like 33 cycles, roughly speaking, right? Or whatever it is, like 33 milliseconds, which is whatever. If you do the math, it will be a huge amount of time. So it will be this multiplied by 2 at 66, and then 66 million cycles, right? Make sense? Okay, so how to build this algorithm? And if we suddenly have a thread number 4 joining us, then what do we do?
Change the timer.
Yeah, in theory. So then we will be dividing by whatever, let's say by 4. So then we can do it 25 milliseconds, right? Or something, right? So far, so good. Okay, so how to build this? How to build this scheduler? Like imagine we have a timer. So what kind of data structure we'll put in a kernel?
Time elapsed. How much time has that process?
Well, just like let's just first consider. Boy, I'm not gonna give you the answer. So can someone recall the scheduler in x6? Someone who took x6 class. It's called round robin. What is this? How does it work?
It's like a circle, right?
It's a circle. How do we build it physically? Oh, like, hold on, like, we have a, like, in x6, it was an array, but if we have a list of threads in the system, right? Your scheduler can have a pointer to the current thread, and when it, the timer interrupt comes in, you just say, look, I will move to the next one, right? And I will move to the next, right? And so on. It's very simple, round robin. So what do you think is not ideal about this round robin scheduler?
I feel like it's difficult probably to balance preemptive interrupting like with the timer versus when this is called like file system read, it's also interrupted, I think is the term for that.
You can get context switch, right? Because we see with I'm blocked and file.
Right, so then something like context switches often will move to the next thing in the list and it'll have barely any time on itself. And so then it's pretty unfair because it'll only get back to itself after you've gone around the whole room.
Okay, yeah, I agree with this. Okay, so let me just say the same one more time. Imagine this process which is currently running, and I will draw it like a slice like this, finish maybe like 10% of its own slice, and then did a syscall, and it's an IO syscall, and it goes into the kernel, and well, at this point the kernel says yield, which means that the scheduler will pick the next process to run, right? And this process will be in a block. So the state of this will be, I don't know, waiting on IO for a while, for quite a bit of time, because if it submitted an IO request to disk, then the disk will reply in quite a bit of time, right? And so, but effectively it lost like, if it was like just 10% of its slice, it lost 90% of its slice. And if it does system calls all the time, then literally just like instead of getting a fair 25% of the CPU, it gets like 0.1 multiplied by this, it will be 2.5% of the CPU, right? So that kind of sucks. So that doesn't work this way. So we need to do something else. So what do we do? How do we improve on this? So, but this is really like this Stroman scheduler in x6. We just organize the process in a simple list. In x6, it's an array, and we pick the first one from the list and like run it. Then timer interrupt comes. We pick the next one and put suspended task at the end of the list. Means that just the task got suspended. We will come back to the task only when we cycle through the entire list, right? How can we fix this at least a little?
Create a sort of hierarchy where like when the scheduler notices that this process yields often, we will try to make it so that this process gets chosen more often as well, compared to something that doesn't yield. So like something that context switches a lot will always be in the first 10 processes that gets considered whenever the yield happens, and then something that doesn't switch that often, or which like runs for a longer time, that gets picked like less often.
Like a time indicator?
Something like that.
Okay. To be honest, this is a little harder to solve, but you tell me as well if you have a question.
If you're a process and you're doing a lot of time, you're going to spend most of your time spending. So perhaps back.
That's a good observation, and this is actually what they're doing. What they're doing is that when the process x6 doesn't do it, but it's a good way to solve it. When you do block on IO, this process gets removed from this list temporarily and gets on a separate list of blocked processes or waiting, right? And it sits on this list. And when it gets unblocked, it gets placed, let's say, in the beginning of the list or somewhere around that area. And maybe it will be given a chance to finish its own slice, right? Make sense? Okay, so that's one problem, this fairness with IO bounds, and we have to come back to it in a second. But also, what's the complexity of this scheduler? Yeah, I agree. Why is it linear? Although it looks like it always goes to the next, which suggests that it's constant.
The complexity for what operation?
For finding the next runnable thread.
That does seem constant.
Well, hold on. If we don't remove the threads, the IO block threads from the list,
Oh,
then it's actually linear because all of this can be like in a waiting state. And then it becomes ON complexity, right? So that's not ideal. If we do remove, the complexity comes back when we want to insert, because you said, let's put it in the beginning of the list. But what if actually, like, it's again, like, kind of agree, maybe.
So you can have something like a heap, right?
What is a heap?
Like-
Heap data structure?
Yeah.
But what is a heap? Tell me again, I forgot. Like,
isn't that like priority queue kind of?
Yeah, like where the insert, sorry, you just, the process to pick is always at the top. And so to pick a process, it's constant time. And to insert the process will be
I think it's longer.
lower.
okay, we might come back to a heap. And again, it's a little crazy to me. I'm not an expert on schedule. Like, what I will tell you is some kind of an overview how the kernel was doing it, Linux kernel. And every time they do make a design choice, hair goes up a little. So because they say, look, it feels kind of a case, but like clearly a little odd. So let's go through those odd choices, and then maybe we'll converge to a better choice. But a couple of things which I wanted to mention here. So fairness is fine, right? So it's a good metric to see everyone a fair fraction. There is this minor complication here that 7 processes might have real-time requirements, which means that they have to run or something catastrophic will happen. Again, it's an unsolved problem and no one knows how to clearly solve it. Maybe like it's like John here was to be a real-time schedule. We should go back and see what he says. Sure. And then you want to balance like latency of how often you get preempted with an interrupt, because you're balancing throughput versus overhead of timer processing. And essentially, you probably in an interactive programs like graphical user interface environments, then you want to like have the time slice to be shorter, because like 100 milliseconds might be noticeable for a user, especially if you're not in the front of the queue and it's multiple of hundreds, right? So, but you pay the price of like processing timer interrupt and making scheduling decisions. So maybe you wanna like a longer time slice for like server workloads where the interactivity is less important. But again, everything here has an asterisk. Like 10 papers, which I didn't read right now. It looks very simple. And then also there's this idea, fairness is fairness, but if you have some background tasks, which kind of opposite real in a way, you say, look, I don't want to interfere with my system and I want them to run only when everything gets idle. Right? So they kind of like almost in the background, like anti-virus, virus scanning or something like that. The question is like, okay, how can you fulfill all of these requirements? And again, I don't think there is a good answer, but let's just at least explore. Okay, so Linux kernel said, okay, sure, like this is clearly not a very good way to build a scheduler. They say, okay, sure, round robin is fine, but they also wanted something what is called priorities, meaning that well, maybe I want to give certain tasks a priority. Again, what does it mean? Usually it means that they want to run faster, like they want to land up like ahead of lower priority tasks in the queue, but again, it's not really clear how you carefully define it. But ON is also not a huge, not a good design choice. Although again, on modern machines, like yes, ON is never a good thing. But if n is small, then maybe you can deal with it, and maybe it's not that bad. Okay, so they came up with this idea of priority-based scheduling. And again, if you start looking at it, at this idea very carefully, you think, okay, maybe it doesn't make that much sense. Let's just go. That's what they did. They say we organize processes by the priorities, and higher priority processes run first, but processes with the same priority are round robin. And hold on, it still means that like they say, if you pick a slice, let's say 100 millisecond or something, right? They say that if we have now, instead of having like a single round robin queue, they have multiple priorities, right? And they say, look, processes with higher priorities will be scheduled first. They finish running, and then we will go. All of them will finish running in a round robin. We just give them a chance to run first, but then we still run everything else in the system, right? Which is a little inflexible because those guys, maybe they are ready to run, but they have to wait for everything else still. In order to avoid ON, they introduced the following data structure. And this O1 scheduler, again, like it's kind of interesting to look at it for historical reasons, because you need to understand that, okay, we used to use it and then they departed from it. They implement this. Okay, if you want this data structure with priorities, with the idea that the highest priority will run first, then they finish running, then you move through priorities, and then you again start running the highest priority, right? How will you build it in such a way that it's all one? For them, that was the problem. At some point, they hit the limit and they said, okay, ON is clearly an overhead. And scanning for this is just not a good idea, because something can be waiting, something can be something else. Like, and this specifically, even if we put waiting, we have a waiting queue and we put the processes here, like maybe it's again according to the priorities and something is waiting, even if this thing gets woken up, like for example, this gets woken up, you insert it back here, for example, but you still have to do a linear scan to figure out, is this the one who has to run, or we still have something higher priority, right? For example. So it kind of doesn't solve ON completely. So how can we solve this ON problem?
If you have a guarantee that the data structure on the left doesn't have any waiting processes, then the process structure could just have like a next pointer that points to the immediately next one.
Right, but then you have to deal with the ones which are waiting.
But those are getting inserted at one time.
Well, but the moment you insert them,
so that insertion should take care of the pointer.
do you want to context switch them to them? Because supposedly, like the question again, I agree with you.
This is still a single thread.
So you
No,
no, like,
I see what you're saying.
no, and you say, look, I'll just insert it and we'll continue with the queue, right? With this data structure. The fact that I moved it from blocked to here doesn't mean that I will start executing it. I will just be going with whatever I was doing. And then you go in the circles and everything becomes O1, right? And that's essentially what they're doing, kind of. Okay. Their solution to this is that this data structure, they introduce a notion of a run queue. This is a run queue, for example. And then introduce the notion of priorities. And they say, look, we'll support 40 different priority levels. And they will manage 2 sets of run queues. It's a little counterintuitive. Why would you do this? But as opposed to whatever you suggested, but maybe there is a corner case. And essentially they say, okay, hold on, we will be maintaining 2 copies of this data structure, and we will call one active and one inactive. So essentially you start running the process from the active one, it runs, you move it to the inactive, go to the next one, run it, move it to the inactive one, and so on until you finish. When you finish running through this data structure, through all the whatever, 40 run queues of this data structure, you say, look, I will just simply flip the active and inactive one, and this one becomes inactive, this one becomes active, and you start running through all these processes, right? And at this point, everything is kind of flowing, but it's very similar to what you were discussing. If you have a wait queue where the process is waiting, different processes are waiting on IO, you have a choice of whether you want to just blindly insert into the inactive one, and then it just doesn't break you all one. Or if you want to, like, there is no elegant way to insert it into a running one because, well, then you introduce a little bit of ON, because if you, for example, this is all empty, you're running something over here, you try to insert it back into this run queue, then you have to say, look, first understand that you were running here, so this one has to run, you can switch to this one, and then do a little bit of scanning here through those priorities. It's still all one because you have a constant number of priorities, and then you come back to those guys again. So it's not a big deal, looks like, right? So even this choice for why to have 2 run queues is not entirely clear, but this is what they did, and it seemed to work for them, right? So they said, okay, so this is just a description of what I was discussing. So pick the first highest priority task to run it, move it, switch the queues. IO is blocked here. Okay, so that seemed to be fine, right? But what did it give you? It gave you priorities, right? So it's an idea that certain tasks will run in front of other tasks. And also the idea that maybe you can encode that priority can also translate to a larger time slice. It depends on how you want to structure it, right? Right. So that's fine. So maybe higher priority tasks have slightly larger time slice and they run for long in front of everything else, which solves some of the problems, right? What's not ideal in this case? What is that we are probably struggling with, or what didn't get solved? And let me see what I have on my slide. You want to put it in the expire first?
Must be if we get a higher priority task.
Yeah, so in theory, and again, it depends on how you want to structure the system. So because in this design, because of this, it depends how you define fairness, right? But higher priority tasks are just run first and for longer, but they still wait for all the lower priority tasks to have a chance to run in a specific whatever scheduling slice, right? They just run it in the front of the queue, roughly speaking. And so at this when you're moving a process from which was woken up, like it was waiting on a disk, for example, or something like that, you have a choice whether you want to put it in back into the active queue to make sure that it runs faster, right? And it kind of makes sense, especially it makes sense for like interactive tasks, because otherwise, if you put it in the expired queue, then they will be waiting for everything else to run, and only then will get a chance to run, right?
Yeah.
That's a design choice, and you can do it differently. I think Linux argues that yes, put it in the active queue. Otherwise, you're not really solving the problem when if a higher priority task does a syscall and doesn't finish its own slice, it's still starving, right? Because if you're always putting it back into an active queue, so it will be waiting for everything else to run, then run for a little bit, does another syscall, and doesn't run again. So it intuitively seems that those tasks should preempt the currently running task and have a chance to run. And no matter whatever your complexity is, land on the active queue until they exhaust their time slice. Like whatever, if we say, look, they should run for 10 milliseconds, for example, and they do a syscall, spend some time on the wait queue, then get woken up, and this queue is still active, and maybe we're halfway through it. Let's put it back in, try to finish their time slice, right? And it will work better for interactive processes like GUI, right? Because then at least you will immediately see like a keyboard interrupt from a user or a mouse move. And then, even if it happens like constantly, you will be constantly bringing it back to this active queue, and then everything like is more interactive for you. Agree with that? So it seems that the same decision here is to put it back on an active queue, even if it breaks your complexity slightly, but it doesn't, right? Agree? So everyone else makes sense? So yes, so if we're waiting, we need to essentially make sure that we put it back on the active queue. And what it gives us is that actually it gives us, like if I switch to this to this slide, you can, for example, start accounting for this time slice, right? So you say, look, you only go to the expired queue when your time slice goes to 0, right? And essentially, if you executed like 1 millisecond out of 10 for your time slice, you go to the blocked queue, you come back, you're always coming back to the active queue with 9 units of time slice, right? And only when you are really exhausted your time slice, then you get moved from active to an active queue, right? Makes sense? At this point, okay, this kind of converges together and like kind of makes sense for everyone, right? This is what Linux was running, right, for a while. What is again not ideal about this scheduler? Kind of like fundamental thing which it doesn't solve.
Yeah, I think the process can change as well, right? So how do you like move it around?
Well,
How do you decide?
it's a good question. How do you decide it? Yeah. I don't think there is a very good way to decide it, right? So I think like for those absolutely background tasks like antivirus software, they should be probably running at the lowest priority, right? Meaning that if any of those interactive tasks are constantly bouncing between wait queue or IO wait queue and back, they will always be running, will always be preempting a low priority task like AV scanning or something going on, this defragmentation or something like that, right? And by the fact, by the way, this is the whole business of those priorities is that to make sure that a higher priority task can preempt a lower priority task. And it's still kind of fair. You say, look, this guy will run for 10 milliseconds, and this one will be bouncing on different IO events back and forth. Maybe like there is a ton of these, which will be doing that, and still they will be placed and back in the active queue until they exhaust the slice, right? Agree? But also, what happens in this case where like they account for different priorities, they show you how to like this is the idea that there is like time is proportional, and this is probably from Linux, but you don't even know whether they how many times they change. So that high priority task takes slightly more time. Priority does correlate with time. But the problem is that there is a couple of things. So they say, what if like they want to implement this idea of giving IO-bound tasks or some GUI tasks a priority boost. So kind of like a temporarily priority boost. So even if it was same priority as some other tasks, which they don't detect as GUI kind tasks, they want to give them priority boost so they can preempt regular tasks just for like maybe some fraction of time. So the question is like, how do you even detect this user interactive programs?
Well, you say many GUI programs are IO-bound. So maybe you could use that statistic as a proxy for which ones are UI. So then you track how many times you're doing it's blocking on IO, and then do the inverse of that, and then that fraction is your priority.
Correct. So what they say, like correct observation, they say they try to use the amount of time you're waiting on something or sleeping, and as a heuristic for essentially to detect an interactive or IO-bound task. And there is like a slight complexity because the task can change. So like in their example here, so they say, look, if you have a GUI program which configures something like a DVD ripping, that's an example from the past. So initially it's GUI bound because the user has to click the buttons, right? Then when it starts ripping, well, it turns into CPU bound because at this point it like runs encoding algorithms and whatnot, right? And you have to actually like switch, and the task can go through cycles of IO bound and CPU bound. But essentially they said, okay, the amount of time you're waiting here is a good indicator that you are an IO bound, and you can like get this temporarily boost, right? So essentially they say, look, we will introduce the notion of this dynamic priority where bonus number is calculated at runtime and based on sleep time. And then you decide priority. I mean, priorities are kind of inverted. So I think what is it? The max is like, if this is 0, then this is minus 39. In practice, it's slightly different numbers because they also have real-time priorities. And so, and the higher priorities have a lower number. So that's why it just subtracts and computes whatever, uses some formulas and heuristic, make sure that, okay, you get a temporarily boost. And essentially, if you have a bonus of 0, then nothing really changes, right? Well, may not be like ideal from this formula, but that's fine. And those priorities do work, so they allow you to make sure that interactive tasks are ready to run. But still, like, what is the biggest kind of problem of this scheduler, which is maybe hard to notice, but specifically what happens when you like imagine this is your highest priority, maybe super duper interactive task, and it exhausts this time slice, and you move it here, and at this point it has to wait for everything else to run, right? How do we do this? what happens to this task? It really does have to wait for everything else to finish, looks like it, in this approach.
But I think their justification is that those time slice is not too high for this low priority process, so it's still fair for the high priority process.
It is fair. Okay, I guess. I mean, to be honest, it's a little tricky to. I mean, I agree with you that it seems if you define fairness that okay, if you exhausted your time slice, then go and go and stop running. But imagine a case in which maybe you exhausted this time slice, but you maybe you ran for like something like 5 milliseconds in the previous time slice. You were waiting on IO for a while, and everyone ran through this thing. You got inserted into this new active run queue, and it still seems that either you're getting this still 5 milliseconds of the left time slice, or like forget about boost for a second. So, and I don't know exactly the numbers, but it feels intuitive that like if you did not exhaust your entire time slice within this epoch of switching between active and inactive, you kind of lost it forever, right? So the past is gone. And Linux has a bunch of heuristics, which I don't understand. They say, I mean, I don't even know them, but they were kind of like similar to this, like temporarily boosts and everything. But imagine managing, like essentially, if you look at the patch stat, they said, okay, we have so many heuristics that, and no real algorithmic foundation for how to reason about them, that at least at some point they stopped understanding what is really going on in the system. And this is when they decided to change the design of this scheduler to something what they called completely fair scheduler, which existed in the kernel from this 2.6, so it improved to 6.6. So it gets like, it was there for a while, and it just very recently got replaced with yet another scheduler, right? So let's take a look at, what is that they conceptually doing here? Again, they introduced this notion of fairness, that in general, the CPU gets a fair proportional fraction of the CPU, meaning if you're running 3 tasks, and each of them in the long run, on average, gets 1/3 of the CPU. And even if you was waiting for a while on this IO queues, you can later on catch up with a longer period of time if you need, right? So essentially, the scheduler kind of like remembers the past better. So essentially, the time you were waiting on IO doesn't like disappear, but you still kind of have it. It's kind of as your credit, right? So go ahead.
What if you do a bunch of, like, I can imagine a malicious process where they do a bunch of IO in very, very short bursts to save up stock for the winter, and then they go and then they use a huge time slice to start up.
Yeah, and I mean it seems like an attack and seems like a possible attack. And I don't know how Linux solves it, if they even can solve it. And but let's just think about how to improve on, like, how to remember the past better, and then we might figure out how to solve this attack, or might not. It's a definition of fairness. According to our definition of fairness existing, the behavior which we described, this long period of time, despite the fact that it causes denial of service, is still fair, because we said it's fair to run for a long time as long as you can, right? But maybe you can like improve the scheduler to say, okay, there's a hard limit and you cannot run for longer than X, right? And I don't think this completely fair scheduler at least in the high level description, which is given online without reading the source code, I don't think it does this solution. I never read the source code. But like the awkwardness of the previous scheduler was this idea that you kind of moving between these two data structures. And it's not really clear how you save the task. The moment you exhausted something, you went on a wait queue. I mean, you exhausted your slides perfectly, right? So you out of 10 milliseconds, you run for 10 milliseconds, and everything kind of works normally, right? So, but if you run for like one, went to a wait queue, everyone else ran, you got the game here. Like they say, did you exhaust your time slides, or are you given like this 11 now or something? So not sure. I don't really know what Linux does in this case. 11 is not ideal because as you say, this attack is obvious and you can run into it. But if you put 9 here because you used 1 unit at time here, it's not also ideal because now you only have 9 out of 10.
Is it really hard to hack?
Probably, I mean, I don't know, honestly. We probably can, but okay. They said, okay, we will implement a data structure in which the scheduling will work like this. We'll again, like maybe I have a slide. We'll maintain the tasks logically as a list. And we'll maintain how much time the task ran in the past. So one ran for 5, and it's in the very beginning of the last list. One ran for 10, then for 15, 22, 26. And I mean, imagine the system ran for some number of time. But you say, look, sir, if this is my view, I'll always give for the task which ran the smallest amount of time a chance to run, right? Because if you say, look, if 5 was this task, it was waiting on IO and time was progressing, it's fair for this 5 to run, at least catch up with 10, let's say for 5 units of time, right? So, and sure, they say, look, let's run for 5 units of time, then it catches up with 10, gets reinserted back into the speed. Let's run for 11. That's just easier. So not 5 units of time for 6, then it gets to 11, then it gets inserted right after 10, and then 10 can run for 1 unit of time, right? Make sense? Then at least, you know, no matter how much time you spent on IO, it's all recorded and we know about it. And in the long run, you will get a fair fraction of a CPU. Right? So what's the problem here with this approach?
Schedule lots of tasks. That way you learn your percentage process.
You're saying that, well, when I say unit of time, it can be like 10 milliseconds, for example, of 1 millisecond. You can choose the slice. And is that the question that you thought that I will be preempting the kernel every let's say, a cycle? No, well,
because I was thinking system, we want to get as much as possible.
yeah, that's correct. So what you're saying is that imagine it's a different problem. Imagine you have a process P. You say, look, and there is another process P2 or P1, P2. P1 says, okay, I'm running 1 thread of execution. P1 was running 1 thread of execution as well. Each one gets like fair fraction, half of the CPU, right? P2 says, okay, guys, I understand that I know the game. Create still that for another threads. And then it's like, or 9. And it gets 9 out of 10 fraction, right? So this is a different problem. You have to somehow introduce, it's a real problem if you create a bunch of threads, like you said. Your scheduler somehow has to react and say, look, guys, we probably want to, and again, it depends. Maybe it's a totally legit behavior, and this is what you want from the system. But on the other hand, you say, look, that this P still gets 50% of the CPU time, and this P2 also will get 50% of the CPU time. And within P, these guys will get whatever, 1/9 of this 50%, right? This is how ideally, this is intuitively how would you like the scheduler to work. This scheduler does work this way, right? Like it's not immediate, not like a stock implementation, but they have an extension for this hierarchy, right? But it's just another angle of complicating things. So you have to make sure that you, at some point, split the CPU time between processes. Maybe what if this guy, for example, it gets more complicated, because what if P4 creates P3, but P3 does some processing on behalf of P2. Now what are you going to do? And you say, look, again, if you equally split between processes, not between threads, it's all like 30% of CPU or whatever. Right? So, but in fact, P3 is working on behalf of P2. And then you need to introduce some kind of like if you want to deal with this, you have to introduce a notion of a group. And then you say, well, the group cannot exceed a certain fraction, no matter what they do inside, right? And it's done in Linux, but you quickly understand that this simple dialogue about scheduling evolves into something like this. And it's totally not clear how to solve this problem, selling it. Right, there was a question.
Yeah, so if you split it evenly between all top level processes, like I'm not talking about P3 because that's a child, you could have it. So if it's just P1, P2, then what's the benefit for P2 spawning 9 threads? Would it be that if the threads are doing IO and they're frequently blocked, then other threads in P2 can make progress while this wait?
The question is that, first of all, are you saying that we already implemented the logic in this scheduler that we schedule based on the unit of a process, let's say? So each process gets a fair fraction. You know, the threads within the process are a fraction of the process's fraction, or really. Why the process would, like, first of all, it's not how normally the system behaves, right? Because I think in a stock Linux, this policy, because you say, look, it depends on who are the users of the system, right? So if it's you who are running the desktop, it's quite possible that if you say, look, I kind of control what's going on, and if I launch P2 and it starts 10 different threads, each of those threads should get a fair fraction of like 10% of the CPU, because this is exactly what I'm trying to do. If this P2 is like if you're sharing a machine between multiple tenants and it's some kind of application as a service, or it runs a VM, then you want to implement this hard scheduling boundaries to introduce fairness between tenants, right? And the tenants can screw up themselves internally in any way they want, as long as they cannot escape the scheduling group, right? In general, why would you create a bunch of threads? Just to like have more compute power? Like, for example, like, I don't know, if you're doing like a compilation run, you say, look, create as many threads as you want, just take all possible CPU time. This is exactly what I want to do right now, right?
Well, it feels like it's no more compute time if it is the fair top level process. But you're saying the real systems are not fair for top level process.
Yeah, so I think Linux in the default setting just uses threads as scaling units in most kernels. But then I think they have this notion of container groups where they say, look, we place those and cap them at a specific unit of time, right? But it gets kind of tricky. Sure, but okay, let's this data structure where we said, okay, we remember the past clearly. No matter like all these heuristics and boosts, which are nice, we believe they not precisely capture the past, and maybe they partially capture the past, but we still like it. We don't believe that it's a very good model, and it's much easier to remember everything. If you run for 11 units of time, we'll insert you between 10 and 15, and then 10 will run for whatever 2 units of time becomes the to become, they call it the media's task. So it becomes not the media's task in the system, right? So what's wrong with this data structure? Good question. We'll come back in a second. Let's just imagine single priority for now.
linear insertion time.
Well, yeah, but it's, yeah, so essentially you say, look, you again, if you have a ton of processes, this insertion, well, again, in this example, depends on how you implement scheduling, right? So if you implement exactly how I said, meaning that you always know the next one, your insertion is always O1, because you say like, I will insert it, the past immediate, right? If you already knew the next task, you know for how long you're gonna run, then you just insert and like this problem kind of disappears. I guess the way they built it was not like that, and they said, look, we will still run the system for some quantum, let's say, I don't know, 10 units of time, and that's your minimal scheduling interval, because maybe you cannot configure the timer in such a manner that you can exactly run for like 1 extra unit of time. It's always 10. In this case, you might end up anywhere in this queue of threads, and then it becomes linear, right? It depends on how. It's important that if you have a fine-grained timer, you probably can avoid this problem and can keep it at the list. You just say, look, deliver the next timer interrupt the moment this task becomes no longer in the list. It doesn't work very elegantly, because what if like you cannot really like, you still need to choose a quantum, because you have to say, look, I cannot preempt my system more frequently than 7x, because you cannot preempt every cycle. It takes me like 5,000 cycles to process the new, right? So you still have a quantum. It can be very small, but still it will be there. So on average, not on average, but in reality, if you have a list of these processes, right, and you say, look, I know that you are the medius, let's say 10. I know that the next one is 11, but maybe the distance between 10 and 11 is so short that it doesn't make, even though I can physically configure a timer to preempt, it just practically not the best. Maybe it's all like 11. It's not the best idea to go this way. And you say like my minimum quantum of scheduling is 10, for example. And you say, look, I will run for 10. And if this guy will be running for 10, then I will reinsert it. I don't know, like after we have 15 and 30 here, I will reinsert it as after 15, right? And if this guy voluntarily preempts the CPU, let's say it ran, instead of it running for the whole 10, it ran, let's say for 2, so now it's at 12, you have to insert it between 11 and 15, right? So, which, yeah, at this point, it can also end because you have to scan the list, right? So, although intuitively it feels that you can always just look at the next task and schedule for 1 unit of time. In practice, it's impractical. You have to choose a quantum in such a manner that the system runs for some time, and then you insert into this queue, right? So ON is not ideal, right? So how to build this data structure to make it better? And you cannot do it like kind of in practice, although in theory you can, but in practice you cannot choose the very fine grain timer resolution, not because the limitation of the timer, but because you just the overheads of scheduling or processing timer interrupts. So what do we want to do with this list to avoid ON insertion? Say again. What?
Make it easier to
Double.
like
Yeah, but how does it help? Because if it ran, you scheduled it for 10 units of time. You schedule this task to run for 10 units of time. Maybe halfway through it locked on IO, and it just said, okay, look, I'm just like maybe you first put it on the wait queue again. It was sitting on a wait queue, and the system progressed. And then you have to reinsert somewhere in the middle, or maybe it did run for the entire 10 units of time without viewing the CPU. And then you have to insert it between 15 and 30, but you have to find the spot, so you have to scan the list.
Well, I was thinking a priority queue or heap would be a good idea, because then that would be logarithmic.
Mhm.
But then you were saying the 10 and 11 are so close, they don't really matter. So then I thought you could do buckets. You could have certain ranges that are treated equivalently, and then it's constant time insert.
Well, until you end up with when everything gets into one bucket somehow, unlike.
Well, then it's round robin, right? Because if it's all one bucket, they're kind of
Yeah.
more or less equivalent, so it doesn't matter.
Okay, they chose a slightly more structured approach. This is okay. Let's represent this as a tree, like you said. And they picked specifically a red-black tree, right? They said, okay, sure. Well, it's ON and well, not ON, or log of n. And it has a little bit of overhead, but maybe in the end they're gonna be losing time even more. I don't have an example of a tree, but essentially they sorted, I forget which numbers. So let's say well, they use the time, well, not balanced, possibly. But essentially they say, okay, we'll always pick the leftmost element in a tree and take it out, insert it back, rebalance the tree, and essentially this way all operations are log of n. We pay a little bit of price, but in the end, this data structure pays back. And it's not a giant tree, so n is reasonably small, so constants are reasonably. Okay, so that seems like reasonable idea, right? And they said, okay, fine. Seems to be. So let's just essentially they say like they have a way of maintaining time. It's not as interesting because there are like lots of low-level details, but at a high level, time is virtual. And the question is like someone was asking, how do they deal with priorities? So how do you think they can deal with priorities?
A different tree for every.
Wow, different what?
Like a different red black tree entirely for every priority, or is that all?
They didn't do this. And in fact, my understanding is that they don't deal with priorities. They said, I mean, their notion of priority here is that they still have a notion of priority, but essentially translates into the length of your slice. So essentially, first of all, I just mentioned that they maintain for each of this process, the time flows at a slightly different rate. And it's proportional to the weight or proportional to the priorities. Essentially, if you have two processes, P1 and P2, and you say, look, guys, P1 is will be occupying because it has a higher priority and higher weight, will be using, that's my intended fairness. P1 gets 75% of the CPU, P2 gets 25, then essentially the time just ticks slower for this guy. So essentially for this guy if this is a higher priority to increment by 1, it will run like 3 times longer than P2, right? And that's fine. So it's like kind of normalizes everything within the tree, but just the time goes differently. And this is the reflection of priorities. Right? And so on average, like, I don't know if I have a good example here. Here are priorities. So like they essentially say the times go, like on average, the high priority tasks run longer and typically become the neediest, which means that they will always gravitating towards the beginning of the tree, right? And the moment they walk on IO, they essentially get moved to the wait queue, everything like everyone else runs, then they get reinserted into the tree, they end up in the very beginning of the queue. And at this point, they get a chance to run because they are neediest, right? So this kind of priority translates to the fact that they have a chance to run ahead of everyone else, right? So that's okay. What I wanted to discuss. But still, there is no, I said, they don't handle priority. There is no explicit way of saying that, you know, priority kind of implicitly translates into the slice lengths, but not who runs first, which is kind of a weakness of this algorithm. And I'm pretty sure that you can come up with the, like, again, if you give this task a higher priority, let's say like 75% of CPU, it say, okay, sure, it's an IO bound task, and then it like constantly spends time on the wait queue, doesn't use its slice, like always gets to run first because it gets reinserted back into this queue. But then suddenly it changes from IO bound into some compute bound, and it has this huge priority and a huge slice. Then this is the attack which you were describing. It has a huge supply of time slice for the winter. It will block the entire system, right? And it's not really clear how to solve this problem. Like you say, you can cap maybe, but like the algorithm itself doesn't introduce the notion of a cap, right? So if you accumulated a bunch of this neediness, right? The whole system moves, those numbers are large and yours is really small. There is no real way to, I mean, the algorithm can say, look, okay, you're really misbehaving. So instead of 10, we'll give you 100, just go back. But it's back to heuristics, right? And so how do you meaningfully reason about what needs to happen in this specific case? Like it's a case-by-case basis, patching everything maybe works, sometimes it doesn't. But there is no elegant way to reason about this, right? And so, again, I mentioned that every time they picked an algorithm, when you read through it, later on you think, okay, guys, really, like the first thing, like, why did you go with these two data structures? Like, okay, sure, you're saving a little bit of time or insertions log n, but this is clearly more elegant. And this gives you priorities, but then and it does like allow you to like run for a little bit, but then again, it's not really fair because if you're losing parts of your time slice, you lost them forever. This one is prone to this attack apparently, which you can accumulate time and then get scheduled. And so, I mean, apparently they did realize this problem. And they moved to something what I don't know how it works, so I have to go read because this one was the state of the art in Linux for many years, and I didn't know that they switched. They did switch. I didn't realize until like today. Essentially, we can take a look and they like see where the Linux is. But okay, for many years Linux was using this. So it seems that if you're building a kernel, okay, the question like. Let's imagine we're building our wonderful little kernel. What do we want to do? Which one?
I like the tree.
You like the tree? Oh, people who don't know Rust cannot write a tree in Rust.
I was looking at the page for this complete and they have a max.
So it
crosses that
does what? Mm-hmm. Mm-hmm. Yeah, but what if it's like still the neediest? It gets reinserted into the head, I would assume.
Yeah.
To adjust the neediness. Okay, I'm not surprised, but and it's good. So, but I don't think it can carefully reflect. Again, maybe there is like a stretch of inactivity where meaning that they erase the past a little, right? They say, okay, like if you really didn't run and suddenly you want to run, we're not gonna let you run. That makes sense, obviously. Right? Okay, my suggestion, like Talia.
Well, you said it would be harder than Rust. If it was a binary key that's balanced, we could do the trick of representing it as an array, where powers of 2 indices are where you are in the tree, and then that requires no pointers and no lifetime shenanigans.
Wait, hold on. If you're in Rust, I agree with you. But if you're a really Rust developer, what do you do when you're coding in Rust and you need a tree?
You get a create for it.
Yeah, you get a create. That's what Rust is about. So you do. I mean, you can get a create for like tree. Whoever wrote it, maybe it's not whoever. How many bugs will be there? It's your problem. My suggestion: let's just stick with round robin. Those algorithms, they are so ad hoc that unless you really have a good use case and you're an expert and you say, look, I spent some number of lectures and read all the papers in the area and I see a light, which apparently they don't see because they keep changing the schedulers and they change to a new one, which we will hopefully cover next time very quickly. But in my view, it's still a big mess. And like I would say, let's not touch it. Like maybe later on in life, you will have to deal with it, but really not today. So the idea is let's just stick with round robin and just go with it. Just forget about all this complexity. None of it makes perfect sense to me. Like this one was awkward to begin with because, and again, like if you start reading, not even the Wikipedia, but the source code, it's almost impossible to parse. So like there is a lot of like if then else cases and custom, like how they could really time. This is probably, I'm guessing from what you're reading, that it's still the same. Like there is no real single algorithm. So let's stick with round robin. There's a couple of additional, like I said, remember, on top of this, you have to build containers if you really want, because otherwise it becomes unfair. Someone creates a bunch of threads, exhausts the system. But also there is a huge problem with this, is that you have multiple CPUs, right? And you say, okay, guys, how do I wanna handle concurrency here? What's the answer? How do you want to build those data structures?
Can a process ever be moved between CPUs?
For sure. When and why? It's a design choice, but why not? Why not to move?
If you did move them, then you could consider them distinct islands and completely ignore them.
Wow. But again, what if like you started on one CPU, you created a tree of processes? The real question which I'm asking, is it a global data structure or is it a per CPU data structure? If it's a global data structure, you're always running into like severe locking problems because you're always trying to access this element, meaning that you're locking it. And essentially, we didn't talk about it, but even if you increment a number, like atomic increment, and this is the number of cores, and this is cycles, the atomic increment doesn't go like this, it goes like this. Like it grows almost exponentially with the number. I forget exactly the formula, but it grows rapidly and like reaches the thousands of cycles here easily, like tens of thousands of cycles. So this cannot be shared, right? So you cannot acquire a global lock in a real kernel and access this tree. So what you end up doing is that you maintain a per CPU tree and periodically rebalance those trees, right? And everything was kind of okay-ish, but again, rebalancing is an intrusive and expensive operation. So you try to avoid it as much as possible, right? And then you say, look, but like there are studies where like the famous paper actually, Alexandra Fedorova from University of, back then she was at Simon Fraser, now she is at University of British Columbia. She wrote a nice paper which goes something like a decade of wasted cores. She makes an argument that roughly 30% of times you have an idle CPU, or like 30% of CPU time is wasted because like one of those trees, everything is idle on a per CPU tree, but there is stuff to run globally in a system, but you just cannot catch up with rebalancing, right? So that's yet another problem, is how to build those things in such a manner that you can somehow rebalance those data structures efficiently, right? And I honestly, I don't know the solution. And I mean, I never was in this field, so that's why I'm like you essentially. I just read whatever they write and trust them. Even read the source code, I couldn't, just too hard. Essentially, that's yet another problem. So that's why I'm saying, okay, let's not even think about it for now. Let's just do a simple round robin, since in our toy kernel, we're just running a couple of CPUs, logs max like 200 to 400 cycles. There's global log on this. You can build priorities if you like. I mean, again, to me, priorities are even confusing, right? And they only work when you have this IO bound task, because intuitively, why does it really help that you run ahead of everyone else? It doesn't really help you if you have to wait for everyone else anyway. It's like the slowest task will determine how often do you run, right? So priorities only make sense when you run for a little bit, block on IO, come back from IO, and again run for a little bit while still everyone else is kind of processing forward, right? But like that's why I'm saying that maybe even priorities don't make sense. And so we can just go with a simple round robin for this project, and just remember that there's a ton of complexity underneath.
For this project, then do we block when every CPU is accessing the round robin?
Yeah, you just put it under mutex, and then get the queue, access the next element, release the mutex, just change the state of the process, like running on CPU, whatever. You don't even have to track which CPU is handling it, just running. Then unlock, then the other guys get the mutex, it's the next process. And they all will have their own kind of like markers, right? So because they will move at different speeds and everything, but that's okay. That's as naive as it gets, but it's the easiest to build, and doesn't, we just, again, it's totally non-trivial to build a good scheduler. And I don't even know that there is a good theory, because based on what Linux is doing. Okay, so just a couple of maybe, I don't know what else I have here. Yeah, so like the same idea, which I said, that CFS, completely fair scheduler, just takes out the blocked programs from a queue, but then just reinserts them back. Yeah, but again, I don't see an easy solution for everything what we discussed. Okay, then probably this is what I wanted to tell you guys. So again, no good answer, honestly. But what's the inspiration here is that if you're looking for a research topic, you don't care, that maybe scheduling is actually an interesting topic. I never worked in it, so I don't know. Even the rules which you want to implement are hard to wire out, if possible, if it's not just derivatives. It also gets more interesting because you have heterogeneous cores. Some cores are more powerful than others, right? You have to implement fairness with respect to CPU time. You want to minimize cache pollution, right? So for example, if you have certain, this is called like gang scheduling, meaning that maybe like it's another concept, but maybe threads of the same process, which access the same, which do something in collaboration, right? They maybe you have to schedule them at the same time to optimize performance. I don't think this is built in Linux, so it's not clear how to build it, right? Because you give them a way to run together, they exchange logs, they progress, Otherwise, if one of them is not running and you're trying to synchronize, there is no real way. Everyone is just waiting for this one, right? So it's very hard. Okay, so let me stop here. So we'll come back. Wednesday, and we'll start talking about inter-process communication.